Today I'm chatting with Sarah Constantin. Sarah currently works at Nanotronics and writes a Substack called Rough Diamonds at sarahconstantin.substack.com. So Sarah, welcome.
Hi.
So you named your blog Rough Diamonds to reflect an aspiration to pursue underrated opportunities. What, in your view, is the most underrated technology that's out there today?
So lately I have been really interested in transcranial ultrasound, focused ultrasound for neuromodulation. So that's a new thing. It's a new research field where you can use low-intensity ultrasound, sometimes outside the head, through the skull, to turn brain activity in a particular region up. And what's exciting about that is that it is a non-invasive way to change the brain and that can reach anywhere in the brain, not just the surface. Previous things have only been able to reach the surface, or they've needed brain surgery. So if you want to do it to a reasonably healthy person, if you want to approach things like mild depression, or if you want to experiment with an altered state or something like that, it doesn't make sense to do brain surgery unless you already have a disease that you would need brain surgery for. But the non-invasive stuff becomes a powerful research tool because it can use it on unhealthy subjects and a much wider range of changing the human experience, really. I think there's a lot of people who are interested in AI and making intelligent machines and, augmenting humans and cyborg shit. We're hitting a very interesting point with the technology side of that, where the manufacturer, the semiconductor side of making these devices is improving. We're moving away from, large single transducers to steerable arrays that are on a chip. Very recently, ultrasound has become miniaturized. This has been a revolution over the past decade in hospitals where you can have handheld ultrasound on a machine the size of your phone. You probably don't experience this unless you work in an ER, but they're experiencing that in ERs. And I think that this and some adjacent new neurotechnologies are going to be very interesting.
So I'm curious, where is ultrasound neuromodulation sort of in the technology lifecycle? Have there been recent breakthroughs that make this something that you get the sense is coming? Is it out there right now and there's not applications? Can you talk a little bit about where you think the technology is and when it'll be sort of commonly known?
So we're at the point where there are a couple startups, there are a couple of human experiments. I'm not thrilled with the human experiments because I think we fundamentally have something that we don't have the application entirely yet. So there's, let's see if it helps with Alzheimer's. And if you really squint and you massage the data, maybe it helps a little with Alzheimer's, but probably not. Or let's see if it helps with people in comas. Maybe. But we don't have the application yet. But we have a lot of validation that the ultrasound effect on neurons is real, that you can, in fact, apply pressure to a location in the brain and produce increased firing rates at that location in the brain. And so the next stage is really to find, well, what's that good for? What do you do with that we care about?
Yeah. I think you have a post where you kind of compare, you talk about why it should be in theory possible, right? And so if we think about caffeine, nicotine, other stimulants that work, in theory, you should be able to, without the drugs, just stimulate the brain in exactly the same ways as what happens when you ingest them, and you get the same output. Would you mind just talking a little bit about why you think, in theory, this is possible?
The really crazy stuff, which that if you're aiming high, if you're a little science fictional, but only a little, is the idea of something better than well. Is the idea that, could you make a more or less healthy person smarter, happier, more focused, sleep better, enter exotic, better than normal mental states, more emotionally resilient, that kind of thing? And I had a post about, why should we think that's even possible? And, what have we seen about the possibility of augmenting a healthy person? Is that even a thing? There's some consideration of something like an Algernon effect of we're already under a huge amount of selectivity to make our brains work well, evolutionarily, to survive, reproduce, understand the environment in the ways that we've needed to. We already have big brains for our bodies, so like, how much further can you really go before, like, you should expect that we have picked the low-hanging fruit. But we know that there are, of the nootropics, or the things that supposedly, make people smarter, make them perform on cognitive tests, the ones that replicate are the boring ones. Caffeine, nicotine, amphetamine. The stimulants make you do better on tests, improve reaction time, improve focus, improve alertness, particularly when you're sleep deprived, but even sometimes when you're not. So this kind of modest effects exist. They're not going to turn anybody into a genius, but you'll see them. It's a real thing. So improvement over baseline, just improve as possible. And then you oftentimes, and then human variation gives you, okay, there are savants. There are people who have extraordinary abilities. There are even people who acquire extraordinary abilities later in life, like after they get bopped on the head and they have calculating abilities or something like that. It happens occasionally. They usually also have trouble. Sometimes you get deficits along the way, but that's the thing. There are some extraordinary mutants who do not feel pain and physical or emotional, who have abnormally positive affect throughout their lives. So the range of what you can get a human brain to do includes some things that are, at least modestly better than well. And that should give us a little bit of hope. And what gives me a lot more hope is the fact that if you look at how well we perform at tasks in life, there are occasions when we dip way below our own norm. There are occasions when we are tired or stressed or whatever, when we are way below normal. And in principle, could we not dip like that? Yeah. In principle, could there be some kind of intervention that makes you on your worst day more like you on your best day? That seems like one should be hopeful about that. I don't want, when I'm speculating, I want to try to stay grounded. So I'm like, if you make everybody like a quintuple von Neumann, I have no idea. I don't know if that even makes sense, but but where we could be most helpful is bringing up your bottom to your top. Maybe that's possible.
I had a conversation with Steve Hsu like late last year that sort of changed my view on the relative importance of different technologies. And so he talked a lot about gene editing and where you could go with IVF and doing selections on embryos, and sort of over time where that could potentially take humanity. And it sort of got me thinking that like it's possible that we look back in 50 or 100 years and feel like the ML models that we ran to understand our genome and some of the like interventions that we do there could end up being more important than like AI technology itself, right? Everyone right now is very hot on AI. I'm curious, like in the broad perspective of when we're looking back for 50 years, do you have a hunch on where neuromodulation will fit in terms of importance?
I honestly think it could rival AI if people do the right research program. AI is obviously very impactful, but I think we're going to run into probably some limits based on data scaling. You can always pile more computers together if you're willing to spend more money. Up to in the past decade, a lot of the improvements are driven by hardware, which is driven by a combination of Moore's law and increased willingness to spend, increased cost per run. So both of those trends probably have limits. Moore's law probably has not quite fundamental physical limits, but limits on our current paradigm of shrinking transistors. At a certain point, the transistor, you can't shrink transistors farther without having quantum effects. If you're going to do better, you're going to have to change your semiconductor paradigm. And at a certain point, we're a ways away from it, but at a certain point, the economic returns to spending more on every training run are going to level off. So I don't know. I've been thinking 3 orders of magnitude on scale before this trend has to stop. At any rate, I don't think you get everything that we care about in intelligence in that paradigm in that, 3 orders of magnitude, maybe this decade, maybe next decade. I certainly don't think you get ASI on that time scale. And then the question is, and then where does AI go from there is much harder to predict. It's not a straight line you're following anymore. It's like, it becomes, there are many, many directions that you could go when just add more cores is no longer the way to go. And given that kind of a framework, then it becomes quite interesting to think, how does that play with human augmentation? You could on a 10, 15-year time frame, you could go from an immature technology to a much more mature one. You could, you don't have time to develop generations of humans, iteratively, from an embryonic perspective, but you do have time to develop technologies that augment, current adults, and get them to the point where that starts to be impactful. It also probably synergizes quite a bit. I'm very interested in how people who are building AIs might relate to doing things to their own brains, and how that might be used to inform how they build the AIs.
Do you know how much funding is going into neuromodulation?
I actually do not know. It's not a huge amount.
It's not a huge amount?
Yeah. There's a couple I was able to find a handful of startups, all of which have under 10 million in funding each. There's collectively, I don't know how much, I'm not sure how to estimate how much funding has gone into academic research, which is a broader thing, but we haven't seen a project backed by a large company. It's early. We're still early.
Yeah, and I'll link to that post, because it was really nice. You kind of laid out like most of the startups that you're able to find and how much funding they had that are in the space. Out of that list, did you have any that you thought had the most interesting use case?
So I'm always intrigued by the people who want to do the weird stuff. So there's people who are trying to replicate meditative states and so on. That's interesting. There's a much closer to home, more grounded sense. There's the forest neuroattack is very interesting. So it's not transcranial. It's inside the head. So it's a little bit of surgery, but it's less invasive than an implanted electrode. And they're going in a much more medical route. But what they're doing that's important is that they're both reading and writing. So they're not just sending ultrasound, but they are also using ultrasound as a imaging perception technique. So because the important thing to do is to confirm that you had the effect you intended. You mess with the brain. Was it messed with in the way you meant to? And you have closed loop control? Can you measure what's going on and adjust in response? Because of course the brain is always changing. This is something that closed loop control is something that electrode implants for epilepsy use. So if they want to give you a little stimulus to stop a seizure in its track, they have to track when are you about to have a seizure and stop that. And you could imagine that if there was some kind of, if you wanted to stop a tremor in its tracks for somebody with Parkinsonism, or you want to stop, or much more speculatively, there's some brain signal that's like, you're starting to have a depressive episode, let's stop that in its tracks, or something like that. You're starting to have an OCD compulsion, let's stop that. Well, you have to detect it to stop it. So that is the difficulty with transcranial ultrasound, is that we don't have a great read mechanism. We have a write mechanism.
Oh, that's really interesting. So I would have thought, and I'm actually curious, for a company that's trying to induce a meditative state, or say they're trying to make you happy or something, just for the sake of argument, I would have thought that how it works is they would put a bunch of people into brain scans and they would read what their brain looks like in the happy state, and then they would try to recreate that with write. But I would think that the read needs to come first. So do I have a misunderstanding of how this typically works? Or yeah, go ahead.
Some of these people have fMRIs going, but right now most of the animal experiments, which are kind of better, are well, if you aim ultrasound to a certain place and you've implanted an electrode in, you can check that it makes the neurons in that place fire more. And you can also confirm if that's the place that controls the pause, the mouse twitching. that you can make the mouse's paw twitch when you send the signal there. With humans, there's like they did like a very basic "is this thing on" kind of study where they stimulate the visual cortex and the people say, "Yep, I saw a bright light," which is exactly the same thing that would happen if you stimulated the visual cortex with an electrode in there. It's what enables you to see all the things you see, but if you just stimulate it, you normally just see a bright spot. So in that case, the confirmation that you did what you thought you did is a behavioral one. But in some cases, they try to do an EEG confirmation that they had the effect, but that's not localized. That's like, we saw a change in the patterns of brainwaves around your entire head. That's very vague. It's not ideal. You can do it with fMRI. That has some problems. It lags what's actually going on by a few seconds. So I'm interested in some other read modalities. You can apparently, at least at the surface of the brain, read blood flow with infrared, and that's much less bulky than the big put your head in an MRI machine. They're starting to be able to have portable things that can read magnetic activity in the brain. So I'm still looking around for this, but one of the hard parts is if you actually want to validate a device, you need to validate that you have the intended effect.
So this might seem kind of like a science fiction-y question too, but it's the first thing that comes to my mind when I hear reading is if it's in theory possible to do a lot of these different like right actions to make somebody experience a certain emotion or feeling or even see like a light, is it also possible to like read thoughts or read emotions in principle?
So this is something where I think we don't know enough to do a lot of that. I've seen countervailing claims. I've seen people claim that they can tell what thought you're mentally verbalizing, like what word you're thinking with an EEG. I still want to check some of this stuff out, but I'm a little skeptical. I don't think we understand what's going on well enough to mind read. We know how to scan where in the brain there is activity. Ultimately, all of the modalities we're talking about are where, and looking at blood flow, or looking at electricity, or looking at electricity via magnetism. But it's like, here's a place in space, and in this location in the brain, do we have something that we think correlates with activity? Oh, you could do glucose. That's PET. All of our imaging modalities come down to where is there activity. What does that mean? Is there a mapping between a pattern of activity and a thought? I'm not sure. Different people have different parts of the brain active during different tasks. So how much of this is common? Would there be a common code to this? I would expect that there are some commonalities in activity. It could be like, well, there's some regions of the brain that are active during language processing. Maybe if they're lit up and the person is speaking or reading or something like that. You could have a task mapping. Probably not perfectly accurate, but like that's plausible. You might be able to have an emotion mapping of like, yes, there are emotional areas of the brain that activity might map to, someone who's upset versus someone who's not, or something like that. A specific thought, like with content, I'm thinking of a white elephant, and then you read out white elephant. That's a much, prove it to me. I haven't seen anything that makes me think that's the thing.
Yeah. So one question is, technology's been a lot more under fire over the last 10, 15 years. So social media caused an uproar, sort of Facebook and Silicon Valley kind of came under the spotlight. And then with AI, it's taken almost to another level where you have people saying, it's going to be politically dangerous or it's going to foom and sort of, wipe out the planet. This also seems controversial to me. I'm curious what you think like the biggest challenges will be from getting public acceptance to technology like this.
Oh God, no, people will hate it. But the thing is, people hate. Journalists hate. Journalists hate a lot of things. Users don't always. People hate AI. Users use ChatGPT. Users use social media. Or they don't. And then they're not on social media to tell you how horrible social media is. So I think from the point of view of you'd like to develop a technology, it probably makes more sense to think about the user perspective, the commentary perspective, because there will be negative commentary. Of course, there will be negative commentary about things. Negative commentary, to my chagrin, is a market, a very popular one. People want to consume content about things that suck all day long. So that can shut you down. But like if it's sufficiently aggressive, I don't have hugely good models of when negative commentary becomes an actual threat to the existence of a technology. Because clearly sometimes it does and sometimes it doesn't. This is an aspect of politics that I don't really understand. I certainly think that there are valid concerns about we should not be manipulating people's minds in ways that are bad for them. I think studying how minds can be moved around and altered is fascinating. But when you get to the point of like trying to make a consumer product, I think there are very valid concerns about, are you making this addictive? Are you cognitively weakening people? Are you giving them something that, is valuable in one sense, but is making them suck at other things? I think we have very good the existing court system will get on your ass if you do an obvious harm to someone. But if you do a subtle degradation, like a lot of people think that they've become, their attention spans have been nuked by social media or something like that. That's the kind of thing which we won't get shut down in a hurry, and like could be a harm to society from some kind of neuromodulation of like a subtle degradation.
It occurs to me actually that this also has a neuromodulation may have an additional challenge that sort of like AI and social media didn't have. So beyond like the ethical or political considerations, it's also sort of like, if not directly a medical technology, like on the boundary of a medical technology. And so much easier for like regulators have a lot of experience with medical products and kind of blocking them. So like from a technology perspective, are there things that you worry could go wrong with this that would halt progress or stop it? Like are there big risks from like a development point that could, get regulators involved early on and kind of shut it down?
So I've been trying to understand this, and it seems like, as far as I can tell, it is de facto, I'm not a lawyer, I'm not an expert, it is de facto legal to have a neuromodulation device that doesn't claim to be medical, that is for entertainment purposes only, because there are all these TCS devices out there, that transcranial direct current stimulation. It's an electrode on the outside of your head. Now, does it, and they say like it's good for focus, it's, calm, whatever. Is it? I'm going to call bullshit. It's a very weak literature. But are you allowed to sell it? Yes. Are you allowed to sell entertainment devices that have an EEG recording component? Yes, you are. They're on the market. Again, it's electrodes on the outside of your head. It's safe. It's not a lot of charge. I put electrodes on the outside of my head. It's unless you put too much voltage in which case you will notice because it stings like a mother. It's a very simple technology. But those things are on the market. They have not been shut down. So just because it's on your head, assuming that you are not making medical claims, which of course are regulated, it seems legal. But talk to a lawyer. Of course, if you are, there is a medical angle to neuromodulation, which isn't should be medical. You can use it to treat diseases. You can use it to replace the really terrible side effects of implanted electrodes, which are necessary for people with severe neurological conditions, and do this in a less invasive way. So I think probably the right way to go about this is two parallel tracks. There will be organizations that seek out medical treatments for diseases, and there may be organizations that are consumer products. And maybe those two things can coexist.
So it occurs to me we glossed over this a little bit at the beginning, but it might actually be helpful to talk about ultrasound neuromodulation, like practically speaking, what are the forms that these products are taking today, and what sort of form do you expect them to take? So you hinted before at like, oh, that device is actually, like implanted into your skull and there's a surgery involved. And you hinted at, oh, there's some that are just, on the outside of your head. Can you talk a little bit about what the different forms of this technology take?
None of these are things are consumer ready or even like prescription doctor ready products. Right. All of them are experimental. All of these are things that are like, this is a startup, or this is something that they've done in academic labs or whatever. The traditional setup in an academic lab is single element transducers. They're big, which are powered by a box, a waveform generator on a cart. and the transducer themselves may be custom shaped to the location in your head that they want to put it on. And they have an MRI scan of your brain, and they have a camera, and they place it in exactly the right place on your head, and turn on the machine on the cart and give you your zaps. And so that's a little bulky. It's kind of one machine, one purpose. It's not. The newer stuff is on a chip. It's fabricated like semiconductor devices. It may be a multi-array that has many ultrasound transducers and is programmable, so that if you have some kind of headset with many of these around the head, you may be able to programmatically type in the coordinates inside the head if you would like to direct ultrasound to, and the waveform, and get that waveform to that place. That is something which there's at least one preliminary device that is ready for pre-orders to academic institutions that is working like that. That is a steerable, programmable ultrasound thing. Still attached to a thing that you have to put on a cart or attached to a chair, not a full wireless walk-around headset. There's a startup that's trying to do lucid dreaming with ultrasound called Prophetic. They have a beautiful mock-up of a wearable device and a tiny little charger, and that is their prototype. That is their design prototype. They do not yet have all the electronics gear into that tiny little form factor. But I've been conflicting answers from my peers as to the feasibility of extreme miniaturization. Some of them say absolutely we can get there. Some of them say we can get there, but it'll be stupid expensive. Some of them say we can't get there. So I'm still learning about this. But that's true transcranial. But you may also have things that need to be attached to your skull. You're not going to cut deep into your brain, but you might want to be on the inside of the skull or right out of the skin or something like that. That is and once again, that's not a consumer product. That's a medical product for medical conditions. But it has some advantages because it's hard to get things accurate through a skull. Your skull distorts sound waves. When that is the right risk-benefit trade-off for a patient, yeah, that makes sense.
Some questions about AI, and you hinted at this earlier when we had the question on where you think neuromodulation will compare. You've tweeted before that AI won't solve biology itself. So there's a lot of optimism right now that once these models get great enough, it's just going to go and sort of do science for us and find a bunch of drugs, and everyone's going to live forever or something. So I'm curious though, how much of a role do you think AI will play in drug discovery? So again, maybe looking back in 50 or 100 years, do you think we'll view AI as sort of like a pivotal change in the rate of discovery for drugs, or do you view it as sort of just like a minor technology and it's really just a scientist doing experiments still?
So if you look at what AI for drug discovery has been, it's been great. There has been rational drug design or some kind of computational drug design, drug discovery for decades. There are lots of models, and if you look at what part of the drug discovery process they are, they're generally saying, I have a target, I have some kind of, usually a protein that I would like to do a thing to. Give me a molecule that I expect is going to do a thing to my target. That is the very first step in drug discovery. It does not replace experiments on animals. It does not replace experiments on humans. It does not replace a lot of in vitro experiments. It does not replace trying that molecule on its target and seeing if it binds in the assay. It doesn't replace one experiment, but they do it computationally. And the AI models, as far as I can tell, this is not super duper my field, hugely outperforming any models we've had before. So, yeah, AlphaFold works. A lot of this protein structure imaging and 3D modeling and so on, and going from and trying to, as far as I understand, map genetic codes to protein shapes and map molecular structures to binding affinities and so on. With a good data set to train on, bigger, better AI models seem to produce better results. You have to make the data set to begin with. And as far as I know, nobody is straight up saying, it works in silico, we don't need to do the experiment. As far as I know, nobody does that. And you wouldn't want to. So in terms of how much time and money are you saving? Maybe not. On the other hand, in terms of how much new shit can you try if you have a better hit rate? I'm being very speculative, but that could be real. That could be huge. That could be like, okay, here's a class of molecules. We were trying that to that target. And then it opens up, and then something in that class turns out to be a drug. Like, this is just a part of the space you're not looking at. And AI told you, why don't you try that? And then they did, and it worked. That's the case in which AI drug discovery makes a huge difference. Is like sort of the best case is you go through the usual development process you always had, and most of your time and your money is spent on the human trials because that's how approval works. But maybe there are a lot more blockbuster drugs than there were before, because you've opened up a new class of molecules or something like that that you weren't considering before. I think that adds up to an incremental change, but maybe a large incremental change. I'm not sure. Like spitballing, if you told me, okay, the value of the pharma industry doubled because they discovered this class of drugs that didn't exist, that they wouldn't have been trying out before AI. Like, maybe. Again, layman speculating, but like maybe. You fundamentally aren't changing how you go about most of the research. You aren't changing how you do target discovery. You aren't changing how you understand disease biology. You aren't changing how you do trials. You're changing which molecules do I try in my assay, in my many well plate. What do I do once I get off my desk and my computer and go to the lab bench? That changes.
Got it. That's super clear. So it seems like there won't be just one day where the AI is out there saying, here's a new drug, it works, go use it. It's going to help with ideas generation process and discovering molecules.
Yeah. I saw a medicinal chemist who was trying to debunk AI and go through his workflow and was like, here, I did this. It took me this many hours, this many days, this many weeks. The AI did it instantly, but pretty much it was what I would have done. Now, unintentionally, this is a great endorsement of AI as a commercial product. It's like, wow, you replaced a PhD, many years of experience worker's time and made what took weeks, 10 minutes. That's valuable. It's not a debunking of AI sucks. That was valuable. But you keep it in scope. But think about scale, scope, everything that goes into making it drug. No, it didn't replace most of it. It replaced a tiny, tiny fraction of it.
I see. Outside of drug discovery, what areas of science do you think AI will be most impactful on?
So when I think about modeling complex dynamics of things where we have adequate data and where mathematical models tend to be, sorry to say, on the weak side, that's where I'm hopeful about AI. So we had a great result recently from DeepMind that was predicting weather. We have a lot of weather data. We know that fluid dynamics is a famously difficult thing to model deterministically, model mathematically. It's one of the millennium problems, Fluid dynamics is hard. And so what if we forget all the physics we ever knew and run it through an AI and see and predict the weather? And it was better than the best models. And that's the kind of thing that I'm hopeful about, and that has industrial applications. So this is one of the things we do at my company, Nanotronics. We're not predicting the weather, but we are predicting turbulent things, complicated chemical things like what's happening in a reactor, what's happening in the reactors that produce chemicals or produce semiconductor wafers, where these are already extremely well-instrumented machines that have a bajillion sensors in it, and they're very smart people at those companies writing tons of equations to model what's going on in those things. And, your equations don't often survive contact with the enemy. And this is something where throw a lot of compute power at it. Maybe it's better than the smart guy with the equations, and it can improve your productivity. I'm also hopeful about that in the world of cell culture. We have a lot of drugs and biologics that are made through industrial cell culture. And industrial cell culture is very hard, and the people who do it will tell you it is more art than science, though they are scientists of years. Predicting what makes your cells grow well versus what makes them, get sick and die, tough. But back in the 90s, people were talking about, well, what if we took images of them? and did image processing and analyzed the images and looked at how healthy the cells are as a function of the conditions under which we treat them. What if we just, and they were like, no, not worth the money. Too much compute power to analyze those images. Well, now it's up the 90s. And now you have NVIDIA partnering with a cell imaging analysis company that I used to work at and making this a scalable cloud service. So, we can go from you have to have a theory because we couldn't possibly just collect data and throw compute at it to now we have the compute, we have the models, predict what you couldn't predict before. You were 20, 30% off predicting before. So I think for a lot of things where it's not even so much science as industrial process where it's like, this is just hard and we have a low yield and it fails sometimes and we don't have a systematic theory for why. Well, maybe that's an AI problem.
In your post on the limits to scaling, you sort of theorize one point that I'm curious to get your perspective on. You predict that once we do reach some sort of limit for these large generalizable models, or generalizable meaning like you ask it a question and it's kind of like equally as good at every topic, like a GPT-4.
Yeah.
You sort of predict that we might end up with more narrow models that are specialized for a specific task. I'm curious where you think this will end up. Are you on the team of we'll just have GPT-5, 6, 7, or do you expect it to sort of pan out and have models that are trained more test specific?
So for now, we absolutely have to face the fact that bigger models trained on more data can be extraordinarily general. I came of age in the 2010s when that was not the case, and the people who bet hard on scale were right. And for now, that is true. And for now, the models keep getting bigger and better because primarily they are trained on more data. The number of people like the bigness of the model is the number of parameters, but there's optimal scaling laws of in order to get the best performance, you need to have proportionally more data when you have more parameters. Otherwise, you just get overfitting. And what we're short of is data. And we're short of means there's only so much data you can scrape off the internet. And that's where the big language models are. They took images, they took text off the internet. They're enriched for what they call high quality sources, which are things like books, journal articles, newspapers, Wikipedia. Part of why they are so good at, I believe, at answering informational questions, like it's a better search engine than Google often, is because the sources you would trust on this many of them are included. They know what the newspaper knows. They know what the journal articles know. Not quite enough. I think there's probably some stuff that's in PDFs or in scanned books or whatever that they haven't really incorporated. But like you might be able to do better by OCRing some stuff. But fundamentally, you got to have the good stuff in there. And the big question internally is simulated data going to improve performance the way increasing amounts of real data is? And I don't know. I'm a little bearish, but that is definitely the question. That is what they are experimenting with. Then the other thing is that not all data is public internet data. And this is part of Metatronic's strategy, and I think part of a lot of AI company strategy is going to be, we're not just a company that trains models, we're a company that creates data. So like factory data, most of which is being thrown away, most of which they don't know how to make use of it, so they're just kind of sitting on it or not keeping it or something like that. Well, that gives you a data set that is not the internet about the dynamics of mechanical and chemical and physical systems. And the more of that you can own, the more you have a data set of that kind. I imagine that a more text-based written AI company that partners with corporations, it will have the data set that is internal corporate documents. And there's a lot of information that is, confidential and locked up in corporations. So I really think that, it's a little bit of a cliche by now, the data is the new oil or whatever, but once you get to the end of public data, then you do have to see models diverge in what they can do because of what additional data sets they have access to. And that's an angle where you need to have divergence. And where you would only see scale if somebody really managed to buy everything there is, and expect that one player is going to be in a position to get one data source, and one player is going to be in a position to get a different data source. The people, these Riverside guys, if they're collecting all of the podcasts, that sort of thing.
Yeah. So this kind of, my read anyways, of your view on whether AI is imminently dangerous is like a direct result of sort of these views that we're getting towards limits of scaling. Do you mind talking just a little bit about what makes you not a doomer?
So it's not even just that. It's when I think about the doom stuff, what do you need for that? You need something kind of like agency. You need something kind of like what's the bad scenario is that a machine does something not accidental. Now, because machines have been able to do accidental harm. Every machine could do accidental harm. Every computer program could have a bug in it that hurts somebody, even kill somebody. A bug in an airplane could kill somebody. That's not the issue. It is qualitatively different and worse and more dangerous if there were a computer program whose harmful action resisted our attempts to stop it. It would be qualitatively dangerous if it not only that, caused some kind of problem, but if it tried to stop you from shutting it down. It tried to stop you from changing it. It designed its bug to evade notice. Just like heuristically, when people get shot and die, it's almost always homicide or suicide, not accident. Intentional harm can be so much worse than accident because accidents you can repair. So that's sort of the picture here of like, that is why we would worry about AI at all in a way that we don't already worry about every other machine. And in order to do that, a lot of the heuristics that are making you think, an intelligent machine might do that, have to do with something with like, well, it might notice that it will achieve its goal better if it has more resources and try to get more resources. It might, and that in itself, problematic. More compute resources. That's one step closer to taking over stuff shouldn't, trying to mislead people, whatever. So that requires something that I think animals have. You don't have to be as smart as a human to have a sense of self-preservation or a sense of self-interest. You don't have to be as smart as a human to have a goal that you will try to pursue even if something thwarts you. But you do have to be smarter than an LLM. There is something I think is qualitatively different between, sense of self, sense of agency, something like this. It's vague, and a lot of people will say, well, you didn't define it, therefore it's not a thing. But I do think it's a thing. I think you can go all you want at trying to predict the next token or trying to predict the test set or whatever, and you can get better and better and better at that, and not get to this. I think we're progressing a long way in a direction that's very interesting, but doesn't have the thing we worry about to begin with.
Yeah. So is your view that like the current architecture, taking transformer models and just putting them on a ton of text data, let's say we even had like 1,000 times more data, a million times more data than the internet, like you think there's no limit to which this thing like takes agency and starts, doing outside of what it's told basically and trying to get resources for itself? Yeah,
that is pretty much my view.
What would a model need to look like for you to be more worried about it catching agency? Like what would be some characteristics that would make you nervous?
I'm not sure I would know from like architecture alone. This is hard.
Maybe from its behavior, if not from the just like.
Yeah, maybe from its behavior. Certainly, if it acquired resources that it wasn't intended to, that would be like an immediate red flag. Any kind of optimization for not being shut down or for not logging off or whatever that wasn't intended by its creators. I don't know. It is kind of hard to look for because this gets into almost psychology. Like it gets into or philosophy where the concepts are a lot less computational. People want to be able to talk very concretely and engineeringly, but you can only talk in those terms for so far before you have to get woo. And everybody attacks everybody who disagrees with them for being woo, but we're all woo past a certain point. and we all have to resort to what we think is going on with people, or what we think is going on with animals or whatnot. But I think like there's something, if you a mouse can get out of a maze. I might worry if a bot could get out of a maze. Well, I kind of could the bot solve mazes? Maybe, I don't know. It gets weird. I think that I'm not a never doom person, but I think that the bad scenarios are not throw more scale at it and accidentally it wakes up and does a bad. The bad scenarios are somebody says, well, this trajectory is laying. I really want an AI physicist. I'm going to build an AI physicist. I'm going to think outside the box, think outside the current paradigm. I'm going to make something that has the spark that humans do, because I really want that AGI. And that is something where, well, if they were competent to do this, if they got their AI physicist, well, they could also get a critter that could come up with a mass destruction or something, that you worry about this. All of the destroy the world scenarios involve some kind of a physical, unusual engineering project that like they weren't assigned to do. And then in real life, when we assign people to do it, things go wrong and they have to cope with unanticipated problems that maybe are tacit knowledge that aren't going to be in text on the internet, and adapt to it using common sense or experience or what we call the knowledge that isn't all written down in text. So if you said, the robot scientist is going to come up with a WMD, I would say, you've got an LLM? No, it won't. If you said I'm going to devote 10 years of my life to make sure I had to have a robot scientist who can cope with all the problems that come up in a lab or come up in a factory and figure out fixes for my machine done broke. Well, if it can do that, it can do things you don't like.
So related to this, you talk about someone wanting to just say, hey, I'm going to like give it human level intelligence or make it more human-like. You wrote a series of posts asking if human intelligence is simple, or is it basically only one thing? Like, is it something that we could solve? Can you talk a little bit about like what your conclusions are there?
So I don't have firm conclusions there. I went kind of like looking for, is there one little change that opened up the mind? And most of the biological evidence went in the direction of no, actually. Primates' brains, our ancestors' brains, have been growing very steadily from long before what they call behavioral modernity. Behavioral modernity being ornamentation, burial, what we think might be language, certain kinds of innovation and tools. I don't remember the whole suite of these things, but the traditional story was that 50,000 years ago, Cro-Magnon man invented behavioral modernity, even though it was we were biologically identical to anatomically modern Homo sapiens for much longer. The data of behavioral modernity keeps getting pushed back. Archaeology is like, the way archaeology works is the origin point of something is the earliest known site where it was discovered. So the longer we go, the more discovery tools we have, the more dates get pushed back. People have been, behavioral modernity is now going back to hundreds of thousands of years. And we're finding out that people were more advanced along rivers and seashores and so on that we thought, where they would be living on shellfish and, in South Africa and so on. So there isn't, the story of like, we anatomically modern humans sat on our butts for millennia and then somehow something, maybe it was a mutation, flourished culture. It's older, it's more gradual. If you look at genetic changes, like what differentiates us from earlier hominids, it's a lot of things that seem to be straightforwardly associated with linear qualitative things, like brain size, synaptic density, things that can, like a variable that can go up or down smoothly, not like we made one change and it was everything. So mostly it's been like, it's a big topic, but trying to look for a smoking gun, it isn't there. It doesn't seem to be there, or I haven't been able to find one. There's been a lot of, what you might have is some kind of a feedback loop where the evolutionary incentive for intelligence, or what we mean by that, gets bigger when our populations get bigger, or when we already have culture that demands it, or something like that. So you can have acceleration without discrete change. There has obviously been more change in human culture in the past 3 centuries than in the millennia prior. There has been, you do have this like, would you, boring, cool, and I don't think that's pure anthropocentrism. I think there's something to that, but it doesn't necessarily have to mean that there is a simple switch or a simple structural change. There's really not a lot of, all the parts of our brain we have in common with other mammals, like the macrostructure, very similar, and if we try to do microstructural genetic differences between us and less intelligent close relatives, everything I could find was a qualitative. This part of the brain is bigger. We have a longer period of development. Yeah, there's more gene regulatory something, I don't remember. Sorry, but it's something that you could see as a slider that you could push up. Is most of what we know about it, really.
Interesting. So you also have a little bit of a background, I believe, in longevity. What do you think the probability is that we solve aging within your lifetime?
I really haven't thought it in terms of predictions, because I don't have a formal background in longevity. I started a funding organization a little bit ago to do some lifespan studies. The field has changed tremendously. We have money entering the field, a lot of which, of course, is thanks to Laura Deming, who started the first aging VC fund. We now have a drug intended to increase dog lifespan in trials, and in some kind of celebrity awards show, they had a shout out to that drug, the winners saying, please FDA approve it, because they want their dogs to live longer. It's coming a long way, and what's inspiring to me is that while there's a lot of noise, the good guys are winning. People who are serious about aging are not just jumping on the bandwagon, are choosing indications that are relevant to overall aging, overall preventative health for the elderly, are going into the clinic. A good sign to watch out for is if they're looking for things like preventing infectious disease in the elderly, overall immunosenescence treatments, or if they're looking at sarcopenia, muscle loss in the elderly, which is not just a vanity thing. It causes falls. It causes real danger. People die of this. And basically, if they're seriously on the track of trying to prolong healthy life, then they will have drugs for indications that most old people get, or they will have drugs that are safe enough for relatively healthy older people to get. If they are fake, they will have like a cancer drug that would be incredibly unsafe to take if you didn't have cancer and the trade-off wasn't right for that. Or a drug for a rare disease that is kind of a model of aging, but again, doesn't make sense because if you're going to have an aging drug, sooner or later, you're going to give it to a pretty much okay or maybe kind of frail elderly person or middle-aged person or something like that. It will be preventative medicine, much as that is a, taboo word because people don't spend a lot of preventative medicine. But if this is going to make the average person stay healthy longer, it needs to be a pretty fucking safe drug, because the average person is going to be taking it before something goes terribly wrong with them. And that's kind of the test for,
I see.
Are you serious? Are you really tackling the big problem? Or are you calling yourself an aging company and nibbling around the edges? And the good news is there are companies that are tackling the serious ones, the serious thing. BioAge is for real, Loyal is for real, and they're succeeding. So I'm very hopeful about that. In terms of solve aging is complicated by its nature. Aging is the least understood thing in medicine because it's not a process, it's not a disease. Let's take the collectivity of shit that goes wrong over time. Let's try to find underlying principles. They're trying. They've got them. Unfortunately, this week is Judith Campisi passed. And she was responsible for one of the most important discoveries of underlying processes, the senescent cells, And so there have been some discoveries of like behind all of these things that go wrong when we get old, there are some commonalities, and you can try to attack the commonalities. But mostly, like, you don't expect to have the whole answer. You don't expect to crack the code. You expect to, eat the elephant one bite at a time. And aging is a disease. Aging is not a disease. Aging is a situation we don't like that we're going to try a couple different angles on. And we've gone from not really trying to fun to try. So predictions are actually not great at what's my 50% over under for when we've, and what would it mean to really cure aging? And will we actually extend the average lifespan in America? That winds up being political, sociological. Do the insurance companies cover it? Do people start taking the drugs? Are we going to see a lifespan boost from just Ozempic, from just obesity drugs? Like, that's not impossible. We could see something. It'll take decades before we really have the data to know if it did something. But yeah, we could. And now that's an incredible financial signal that metabolic drugs are worth paying attention to, worth investing in. And that I'm hopeful about. Actually, yeah. No, I do think 30 years down the line, we'll see that something that new has come out has boosted lifespan.
Interesting. You've written a post about cancer research as well, and you kind of note how despite tens of billions of dollars on cancer research every year, the progress in combating it is actually slowed a lot since especially the 50s, 60s, 70s. Is cancer research doing something avoidably wrong? Is this something that we could fix right now?
So a lot of that, I was going to write a book about cancer and then and how it's all fucked up, and then the research, actually, the news changed. It got better. So the original huge improvements in cancer therapy, the original discovery of chemotherapy, this was general cytotoxic chemotherapy. It kills cells. It kills the cancer cells a little faster than it kills the rest of you because the cancer cells are dividing faster. But basically, it's not specific to type of cancer. It's not targeted. It's not based on the usually misleading assumption that you have found the right, you have found the one true thing to target. Targeted therapy was the reigning paradigm for a long time. And it was we're going to find a drug that attacked some kind of receptor on the surface of cancer cells that's more prominent on the cancer cells than everything else. That was, 90s, 2000s, 80s a little bit. And those drugs were blockbuster drugs, some of them, and really didn't extend life because it's just such a noisy signal. What's on the surface of your cancer is also on the surface of other things. Not always on the surface of your cancer. You get evolution. You say, oh, I'm going to kill the cells that have this, but what about the cells that don't? Well, those are the ones that survive and come back, and that's where the tumor goes. And so it's not that it's a stupid paradigm. It's not that, but just even sitting on your butt before you've done an experiment, you kind of know that there are going to be limits to it. What we've seen recently in immunotherapies and cell therapies, which are very difficult, which are, one, you've got B-cell lymphoma. Let's kill all the B cells. Can't have B-cell cancer if you don't have B cells, and that kind of thing. Which, while it's very rough on the patient, does work. And then there's, well, you basically have cancer because your immune system wasn't doing its job at killing cancer. Let's amp up a part of your immune system so it kills it more. And that also works. That also has you'll see it in the lifespan result, in the survival results. Now, mostly you see this mostly this matters for blood cancers. And they haven't gotten cell therapies to work in solid tumors yet, though that's the dream. But it's real results. It's not, if you squint a little, you live 2 weeks longer kind of thing. And ultimately, I am hopeful again. I am hopeful about the world of modified cell therapies, if they manage to figure out how to do solid tumors, that'll be huge. What are we doing avoidably wrong? To some extent, it's a funding situation. We went from having a system that was a national lab, mostly of World War II veterans who had the memory and the sense of urgency of wartime science, working under one roof. And they did that, and then that changed to a extramural grant situation where the government would fund various universities and research centers that send in grant applications. That transition happened around the 70s. It happened with the war on cancer, and there have been major critics of that system among cancer researchers, including James Watson, who said that by adding that level of decentralization, you necessitated a level of bureaucracy. You no longer had a common institutional culture. You incentivized people to do basic research and to get funding for basic research, like exploratory science and regular hospital treatment, as opposed to cancer research, the search for cures for cancer, because people were doing this other stuff anyway, and this was a way to get funding for it. So they muddied the waters between three kinds of activity, all of which are necessary. You need to do science, you need to treat patients, you need to try to discover cures. But the third one is something that tends to disappear when you aren't very brutally selecting for it. They used to have laymen on the boards of the National Cancer Institute to make sure that what they were doing at every moment was, are we curing cancer? I'm not a scientist. I don't know. I don't care about science. I want grandma not to die.
I see.
Ask the dumb questions. Are we really getting grandma not to die? And some of that has been lost. So there's been some institutional change that there's a lot more money in research, which means you don't have to be as good to be a cancer researcher. And there's a lot of incentive to get into it because there's more way to fund it. And, so there's that kind of a story of maybe we should not have gone in that direction. And then there's also sort of a first principles thinking kind of a story of if you were going to try to as efficiently as possible use the time and money you have to avoid as many cancer deaths as you could, how would you go about it? You would try to find commonalities between cancer types. You would try not to specialize to hell, because if you thought that was at all promising, you would try to do things that, like radiation therapy and like chemotherapy, are common across cancer types, so that you're not spending all your money on one tiny subtype that has 5,000 patients. We don't have that kind of a strategic priority because there is nobody who is the czar of cancer saying we're going to do it that way. We have a bajillion research institutes and so on, none of whom think in terms of let's try to get the most done with the money we have. They think in terms of, well, we'd love it if our grant doubled. That's winning. So there's certain strategic attitudes that you would expect if there were a guy trying to do cancer research. You don't see when there's a decentralized ecosystem of agents trying to do cancer research and also get paid for it. So would it really work better to have a guy who was in charge of all cancer research? Well, maybe not. Maybe if the guy was no good, they would screw it up worse than the current system. But there is a case to be made that we have some messed up incentives here. And there certainly is I think there's a narrative of you'll never cure cancer. A cure for cancer doesn't make sense because cancer is not one disease. And of course cancer is extremely diverse, but we call it cancer because cell differentiation disappears and cells proliferate and they take over the body. So why aren't we thinking more about those commonalities? Why is it so taboo to talk about curing cancer? Not in terms of over-promising, but in terms of how much of cancer could you cure with one mechanism? We don't need to hyper-specialize. Again, not a biologist exactly, maybe that's hard, but it also seems like we ought to be trying. There's suggestive stuff I've seen about cancer cells are more negatively charged than non-cancer cells across tumor types. Not a lot of follow-up I've seen on that, but oh, if you could detect what's cancer versus not cancer with a short nanoparticle, or something very simple like that, that's huge. Put your poison where the cancer is and not where the cancer isn't. Or a startup I know about that's trying to target P53, which is a gene that is mutated in most cancers. It's not a cure for cancer, but it's a cure for it would be a cure for a hell of a lot more cancers than most things are, because it's 50% of cancers. And yeah, the size of this, the size of the impact is usually not a metric that gets tracked very much. Intuitively, I would expect, as somebody, who knows patients and so on, as a human, I would expect that would be a thing you track.
Yeah. So shifting gears a little bit from a little bit more of the science-oriented questions, I have some old blog posts that I dug up that one of them I really liked and I wanted to ask you about. So can you talk about why you believe that aesthetic judgments are a kind of moral judgment?
Oh man, that was old school. Do I still believe that?
Do you still believe it? Let's start with that, yeah.
So I would not state it this strongly. I would say I was universalizing a lot harder in those days than I do now. I would say that it's not silly to think it. It's not silly to think that when you talk about what you prefer, what you prefer aesthetically, that is part and parcel. You're pointing at something which you say, I don't know why I like it, I just like it. But that's not, in general, totally isolated. People aren't totally isolated. There is some underlying sense of what you value, which may fold over or be part of the shape of how you conceptualize the world that winds up being connected to deeper things. What do you prioritize throughout your life? What is? And you may not be able to, even when you can't explain exactly why you like a thing, there may be something symbolically or in the way your mind is constituted, connected to the things that you just like the look of, and other deeper things throughout your life. Like, there is, I happen to like biomorphic curvy things that look like life. I also I also find that I'm interested in living things sort of intellectually and across stuff. And I also find that when I think about, what seems worth pursuing, what seems motivating is, what seems worthwhile is, good lives for living things. I was clearly motivated to have kids. I'm clearly interested in biology. And there's something that just feels like a yum to me about lush life. And it's pretty obvious perspectively, you can't prove these things, but that there is a connection between the things that I just like the look of and other deeper structural things. Now, it's not always the case, I don't think, but I think that if it's a very consistent preference and you think about, well, what might that mean or what might that correspond to, there might be something connected to it. And I think I think what I would disagree with now, I think I would no longer say that it's straightforward to interpret, oh, you told me you liked this piece of art or whatever, or you didn't like that. That tells me something about who you are as a person, because that's not enough information by itself. That's what did it mean to you? Why do you like it? What else do you like? What is the pattern here? And, does it connect to a through line in your life? Does it through line any priorities, or is it very, very much a one-off and not that important? It's doesn't relate to anything else. But I think you need context. I probably made some overconfident statements in the blog post about and people you like this really gloomy piece of art, you're a negative person, that kind of thing. No, it doesn't mean that. But give more nuance, give more detail, give a pattern, give an interpretation. Yeah, maybe it tells something. Especially the more it matters to you, the more it matters to you. And the more it's integrated with the rest of you.
Yeah. So we're coming up on time here. One last question, Sarah. If there was a really bright 14-year-old that wanted to understand the Sarah Constantin view of the world, what would you tell him to go read or do?
Linear algebra. I came up in math. I'm a putrid pony, and I would not be the same person hadn't studied the math. And yeah, linear algebra in particular is like, it's not just how I think, it's how a lot of people think, but it's just huge, qualitatively different before and after. So, yeah.
Awesome. Well, Sarah, you've been so gracious with your time. Thank you so much for coming on.
Thank you so much. Thanks for organizing.